Dear students, in this class 10, let me write in the beginning some figures. What you know already from your 10th standard class. So just observe. I write first figure like this. Say, you can say what it is. In ray optics, this shape is called as convex lens. And I write this second shape. Just observe. This is the second shape. Can you tell me what it is? It is the concave lens or biconcave lens. Say if I write like this, it is plano-convex lens. And if I write it like this, say this is plano-concave lens, and you can think of this shape. This is called as concavo-convex or convexo-concave or crescent lens. Now can you tell me what it is? If I write like this, what it is? In fact, it is simply a glass slab. So can you make out the difference between these lenses and this glass slab? Thereby you can generate the definition for lens. Observe, as you have already guessed, say in these 5 figures which are constituting lens there, at least one surface is curved. But in this case, no surface is curved. That means a lens is an optical medium bounded by 2 surfaces of which at least one is curved. Say lens is an optical medium bounded by 2 surfaces of which at least one is curved. One is curved. We learn some definitions regarding the lens now. Say, first of all, we consider a convex lens like this. Say, the line passing through poles of the 2 surfaces may be called as, say, principal axis here, like this. This is the principal axis. And when a parallel beam of light falls on the lens, it converges to a point on the principal axis. Say like this. It converges to a point on the principal axis. This point where it converges is what we call as principal focus. In contrast to the mirror, observe carefully here, if the incident beam is from left side, it creates a principal focus on the right side. If incident beam from the right side, then it creates a focus on left side. That means there are 2 foci for the lens. Now, we define this principal focus. Whenever a parallel beam of light falls on a convex lens, it converges to a point on the principal axis. That point is called as principal axis. Say, if we take a concave lens, what will be the definition? We just think of it. Say this is the concave lens. We know in the concave lens, the light diverges. Therefore, we write like this, say principal axis again. And if I write an incident beam from left side like this, parallel beam, then it undergoes a divergence like this. Then it appears to come from a point on the principal axis on the left hand side. This point is called as principal focus for the concave lens. Observe, in the convex lens, the light ray actually converges to a point. In case of concave lens, light ray appears to come from a point. Therefore, we can go for the definition of principal focus like this. Say, principal focus is a point on the principal axis to which a parallel beam of light ray converges after falling on the convex lens or appears to diverge from after falling on the concave lens. So, just go through the definition once again. Principal focus is a point on the principal axis of the lens to which a parallel beam of light ray converges after passing through a convex lens or appears to diverge from after passing through a concave lens. This is the definition. Now, so we have defined the first thing, principal focus. Next definition is what we call as optic center. Optic center. It's a point on the principal axis inside the lens. When a ray of light passes through that point, it will not undergo deviation. That point can be visualized or can be thought of using this figure. Let me write the figure first like this. Say, this is the lens and this is the point on the principal axis. Now, a beam of light falling on the lens like this, if it passes through the point on the principal axis, then it comes out without any deviation. Just sidewise shifting may be there like this. The directional change is not there. If it is a thin lens, that means the thickness at the middle is not very much compared to the thickness at the edge. In case of convex lens, in case of concave lens, thickness at the middle is not very much differ from the thickness at the edges. In both the cases, it is the comparison of the thickness. Then we call them as thin lenses. Say, in case of thin lens, a beam of light falling on the lens will come out without any deviation at all. Say, if we write the lens like this, if it is a thin lens, then a beam of light falling on the lens will come out without any deviation like this. Then this point, what we call as O, here also this point is called as O. That is called as optic center. Optic center is a point on the principal axis inside the lens. When light passes through that point, the light will not get deviated. This is the definition of optic center. And in case of lens, all the distances are measured from the optic center. So to just recap, we just go through two definitions what we learned. First of all, principal focus. A point on the principal axis to which a parallel beam of light ray converges after passing through the convex lens or appears to diverge from after passing through the concave lens. Next definition, what we learned is optic center. It's a point on the principal axis inside the lens through which when a ray of light passes, it will not get deviated. That is, when a ray of light passes through that optic center, it will not undergo any deviation. This is the definition of optic center. And all the distances are measured on the principal axis from the optic center. Next, we want to learn another definition. Say, the distance between optic center to the focus is what we denote by small f, and it is called as focal length. Focal length. the focus which is on the side of the incident beam, say in this case this one, or in this case this one, is called as first focal point, on the focus on the other side of the incident beam, that is on the other side of the lens, is called as second focal point. So the focus which is on the side of the incident beam on the side of the source is called as first focal point, this one, and on the other side of the lens is called as second focal point. In case of concave mirror also, concave lens also, on the side it is first focal point, on the other side it is second focal point. Many of us wear specs. How the specs are created, how the lenses for the specs are made, that is created by using a formula called as lens maker's formula. Lens maker's formula. This we want to derive now. An easy derivation, say by using curved surface refraction formula. We know the curved surface refraction formula is N2 by V, N1 by U, N2 minus N1 by R. Okay. Now we draw the figure for the lens and then we go for the derivation. Say this is what I call as lens there, what I take as lens. The lens is surrounded by the same medium on both sides. So first and first, the lens medium I call as second medium, and surrounding medium refractive index is N1 on both sides. Lens medium refractive index is N2. Now we draw the principal axis there for the lens like this. Now we imagine there is a point object O. The light ray from O travels onto the first face, say like this. This is the first face. At M it falls on the lens. Then the ray undergoes one refraction like this in the lens medium. At N it comes out of the lens and second refraction takes place to form the final image I like this. Now we mark the distances. If this is optic center, this is V and this is U, the object distance. With this figure, we start deriving the formula for lens, that is lens maker's formula. How we go for it? We do this in two steps. First step is to consider only first surface, that is left side surface, and left of that surface is surrounding medium. To the right we have only the lens medium. I write like this. Just imagine this is the left side face and this is the principal axis. If there is only the one surface, the refraction takes place at M and it tries to form an image. Say we extend this because N refraction at N will not be there and it forms an image I dash in the medium N2. That we write separately now. Say this is the left side surface. The object, light from the object will be like this. Once it undergoes the refraction, it moves straight as there is no second medium and it forms an image I dash at V dash as we said previously. Say this is V dash. Here also this is V dash. Now we apply curved surface formula for this. Say left hand side is N1, right hand side is of medium N of refractive index N2 there. So here image space is N2. Therefore I can write N2 by V dash minus N1 by U equals n2 minus n1 by r1. The first surface or left side surface radius of curvature is r1, and I call this as equation 1. Next, this I dash acts as a object for the right side surface, and it forms a final image I in the medium of refractive index n1, that is in the surrounding medium. In that case, I can simply write this formula with these things. Say I dash acts as object for right side surface to form right side surface in medium of lens to form final image I at V in N1. Therefore, we can write the equation like this. Say here image space where the image is formed is having the refractive index N1, and the distance for that is V minus where the object is there, it is N2 I dash in the N2 divided by its distance is V dash, and formula is N1 minus N2 by R2. R2 is the radius of curvature of the second surface. So this is our equation 2. To get the final equation, we have to sum these two. Equation 1 and 2 will get, say, N1 by V minus N1 by U as N2 by V dash, and N2 by V dash cancels there in 1 and 2. And on the right side we have N2 minus N1 by R1, N2 minus N1 by R1 minus plus N1 minus N2 by R2. And taking N2 minus N1 common factor, we can simply write N1 1 by V minus 1 by U. On this side, N2 minus N1 into 1 by R1 minus 1 by R2. With this, now we can simply write the final, next equation. 1 by V minus 1 by U is N2 by N1 minus 1, 1 by R1 minus 1 by R2. So to simplify this equation in the last step, we go for it like this. Say we know in case of lens formula is 1 by F equals 1 by V minus 1 by U. Here, if U tends to infinity, that means we move object farther and farther towards infinity, then the image distance approaches F, because we know when object is at infinity, image is formed at the focal length. Therefore, 1 by F equals 1 by V. Now, if we go for this situation in the preceding equation, instead of 1 by V minus 1 by F, I write 1 by U, I write 1 by F equals N2 by N1 minus 1 into 1 by R1 minus 1 by R2. This is called as lens maker's formula. This is called as lens maker's formula. This lens maker's formula has a speciality, and that is what we want to think of. 1 by F is N2 by N1 minus 1 into 1 by R1 minus 1 by R2. And it is valid, even though we have derived it for convex lens, it's valid for concave lens also. But we know for convex lens, focal length is positive, and concave lens, this is for convex, and for concave lens, focal length is negative. And we must remember the R1 is the radius of curvature of the first face from the left side, that is on the south side face. Radius of curvature is R1. It is positive because towards right. And R2 is negative for convex surface, convex lens. So therefore we write R1 is positive and R2 is always negative. For concave, say R1 is negative and R2 is positive. Why? We just think of it. Say for convex lens, observe from this side, this is the first phase, this is the second phase. First phase radius of curvature is like this. Second phase radius of curvature is this way, R2. So once the incident beam from the left side, R2 is measured in the opposite direction. Therefore, R2 is negative for convex lens. R1 is measured in the direction of incident beam. Therefore, it is positive. And focal length is also measured in the forward direction. So, F is also positive. But for concave lens, we write, say, this is our concave lens. And in this case, as the ray of light travels from back side, say like this, the radius of curvature of the first phase, this one, R1, which is measured opposite to the incident beam. Therefore, R1 is negative and R2 measured this way. Therefore, R2 is positive because it is in the direction of incident beam. And its focal length is always negative. Because R1 is negative, R2 is positive means overall sign will become negative. Therefore, focal length is negative. And also, convex lens or the converging lens need not act as converging lens in all the situations. Whenever we immerse the convex lens in a medium whose refractive index is more than the lens medium refractive index, then that convex lens behaves as a diverging lens. In the same manner, a concave lens, when immersed in a medium of higher refractive index, behaves like a converging lens. Therefore, always convex or concave, the converging or diverging cannot be said so easily because it depends on the surrounding medium. If surrounding medium is air and lens medium refractive index is larger, then convex can be called as converging lens, concave can be called as diverging lens. This is all for this session.